happy to introduce our first speaker, Nadia Gurevich from Ben-Gurion University, and she will speak about Fourier transforms on basic affine spaces of quasi-split groups. So, yeah.
Okay. First of all, thank you very much for the invitation. It's my first talk on this conference. So I will talk about Fourier transforms on basic affine spaces, and this is a joint work with David Kashdan, from whom I learned so much, both mathematically and personally. The Fourier transform of basic affine spaces have been considered by Gelfand and Garaev in '80s for split groups, so I better start with the setting because Fourier transform have been generalized on so many different ways. So I'll start with a split group. The GBS split reductive group over a local field F. You can think of your favorite group, for example, the group of invertible n by n matrices, GLN. And such a group always admits a Borel subgroup, which in case of GLN will be just upper triangular matrices, with a natural decomposition into as a semi-direct product of unipotent radical U and the maximal split torus T. So what is a basic affine space? It's just a quotient of G by U. And such a space has a unique up to a constant G invariant measure, which we fix once and for all. Okay, so the group G, the reductive group, together with its torus, acts naturally on the space X. Just geometrically, and hence G acts naturally and T acts on the left because it normalizes U, and hence the action gives rise to an action on the Hilbert space of square integrable functions L2 of X with respect to this fixed measure, which I will omit from now on. And as you see, the action is geometric. We introduce extra modular character delta B just to make this action unitary. So we get a unitary representation, and by a general result, any unitary representation admits a decomposition as a direct product of irreducible representation, as a direct, as a direct integral of irreducible unitary representations of G times T. The integral is taken over some measure space, and we are interested to understand in every particular case what this measure space is and which representations HX so-called weakly contained inside the representation L2 of X. Okay, so before saying explicitly which representations occur, I will say a couple of words about representations of G times T. Okay, so T is a commutative group, so any irreducible unitary representation is just a unitary character. And the set of all unitary characters, X hat of T, has a structure of a real variety, so on which we define there is a natural measure, which is just a Lebesgue measure. And in addition, there is a Weil group, which will play a big role in my talk. Weil group is, which in the case of, it's a finite group, which acts on the torus and hence also on the set of the unitary characters. In case where our group is GLN, the Weil group is just a group of permutation matrices. So let us just note that since Wx on T, we can consider a semi-direct product, T with W, and for any unitary character, the induction from T to T times W gives a unitary representations. And in fact, any unitary representation of this finite extension T times W is either such representation, tau of chi, or any of its component in case it's reducible. Okay, and similarly for any unitary character, there is a standard construction of unitary principal series. So starting with the character of chi, we extended chi of t, we extended to trivially to a character of the Borel subgroup, and then induce obtaining a unitary representations, which we denote by pi of chi. Okay, so the representation pi of chi and tau of chi enjoy some common properties. In fact, for almost all irreducible character, they are, for almost all unitary characters, they are irreducible. And in addition, they are not all distinct. In fact, for any two characters belonging to the same orbit under the Weyl group, the representation pi of chi is isomorphic to pi of W chi, and the same is true about tau. All right, so these, the representations chi, tau of chi, and pi of chi will be all relevant representation to the decomposition of the space L2 of X, which I started with. Okay, now we can describe the result. The result that the space L2 of X is a direct integral of unitary representation. The integral is over the set of unitary characters. And the relevant representations of G times T are chi times pi of chi. Okay, so this is a satisfactory answer, but note that if you look just as a decomposition of G model, this is not a multiplicity-free decomposition, because pi of chi and pi of W of chi is in fact the same representation. So the correspondence between representations of G and representation of T is not one-to-one. A priori, nothing wrong with that, but it is not as nice as one could hope for. So the goal would be to extend the action of G times T, which is so natural on the space, to the action of slightly bigger group, precisely of, we replace T by its semi-direct product with W, okay? So we still don't know how to do that, but assume we did. And we would expect that, so our goal is extended to such way so that as representations of this bigger group, L2 of X is a direct integral over W orbits of unitary character of T, and the relevant Hilbert spaces, unitary representations of this bigger group will be just pi of chi times tau of chi. They are both reducible. They both enjoy this property that they are equivalent whenever we take characters in the same double Weyl orbit. And this defines a one-to-one correspondence of isomorphism classes of representation G relevant to this decomposition and representations of T times W. So this is in fact a very common phenomenon in representation theory, that if you want to find a correspondence between representations of two seemingly non-related groups, you better find some space on which both of the groups act and in a commuting way, and try to decompose this representation. And if you are lucky, you will exactly get the one-to-one correspondence between representation, sometimes between subsets of these representations. Okay, so the similar idea stands behind the theta correspondence and many other beautiful correspondences in the representation theory. Okay, any questions?
So maybe just to understand, here you already have a clear correspondence just by parameter high, right?
Exactly. I mean, I hope to, because the goal would be to extend the action from G times T, which is transparent and was given to by the very explicit formula, to the action of these bigger groups. But when it is done, one hopes to such decomposition, and in fact has this decomposition. Okay. All right. So now let me be very specific about these goals. So what we are looking for explicitly. We basically, for any element of the group of the Weil group W, we look for an operator which we denote by FW. So this is an operator on L2 of X, and this family of operators must satisfy. So first of all, they should be unitary operators, obviously. Second, those operators must commute with the action of G and kind of anti-commute with the action of the torus. Okay, I remind you that the action of G and torus are very explicit. And three, they must indeed define an action of the Weil group, meaning what's written here, the composition of F phi W1 with W2 must be exactly phi of W1 of W2, where the product is taken inside the Weil group. Okay, so that's what we look for. And now, of course, we should start with the simplest example, which is the group SL2. Okay, to explore what we actually have in this case. So the group G is the group SL2. I want to look at it as a groups of operators of determinant 1 on a two-dimensional vector space V over my ground field. In this case, G naturally acts on V with two orbits, zero orbits, non-zero orbit. And the stabilizer of any vector in a non-zero orbit is exactly unipotent radical of the Borel. So X can be viewed as just non-zero vectors in V. When we consider the L2 space of square integrable functions, it makes no difference. So we can as well think of L2 of X as functions on square integrable functions on V. Now, the Weil group contains two elements, the trivial element and the unique non-trivial element W. So the trivial element will act by identity. The non-trivial element must satisfy, okay? Well, it must be, first of all, a unitary operator and an involution, because the Weil group has just two elements, so element W is of order 2. And second, it must commute with the action of SL2 of G, and as I say, anti-commute with the action of T, and T, which is isomorphic to multiplicative group, acts just by dilation. Okay, so there is a, well, when you look at these three properties, which must be satisfied, unitary plus involution plus equivariance, you quickly come up with the natural candidate of it. And it will be just Fourier transform. Okay. So Fourier transform is a standard operator, so you probably will object that the usual Fourier transform is not an involution, it's rather an operator of order 4. But if we make a slight variation, namely in the definition of the Fourier transform, use not the quadratic form on V, but rather a symplectic form on V. Fortunately, our V is two-dimensional vector space and hence afford such a symplectic form, then we'll exactly get an involution. Okay. By the way, note that the operator FW also being a natural candidate is not uniquely defined by the properties above. However, we'll later see how it arises. Exactly the Fourier transform kind of arises more naturally than any arbitrary operator satisfying these properties. Okay, so we agree that in the case of SL2, the construction, the extension of the action exists and is given by Fourier transform. Any questions? Okay.
Sorry.
Yeah.
What is psi? What is psi here?
Psi here, oh, sorry, psi is is in the real case, it's any additive character of the field. Okay. Well, not exactly any. I mean, in order that this representation will be unitary involution, you better choose psi in the case of local field of conductor 0. Okay, but all right. So this construction, now we want to generalize this construction from SL2 to any split group. And this is possible because any split group is in a sense glued from many copies of SL2. Well, I don't want to present to you general construction, not that it is very involved, but I'd rather look at the example of rank 2 group, in fact, SL3, in which it will be transparent how those Fourier transforms, two-dimensional Fourier transforms give rise to the operators phi corresponding to for the bigger group. Okay, so let me consider the case G is SL3, or in other words, SLV, where V is three-dimensional space. In this case, it is nice because the space X, which is G mod U, in fact, has an explicit model, which I will present in a moment. So now, notice that G acts on V and also on its dual space, okay? In particular, we can consider a space, a set of pairs of elements, vector and covector, both non-zero, such that their natural pairing is 0. So by definition, G preserves this set. And in fact, it's easy to see that the stabilizer of, it acts on it transitively, and stabilizer of any vector is exactly unitary, unipotent radical of the Borel. So Borel subgroup, so X, the basic affine space is identified with this set. Okay, so this set has two projections, to V natural projection, to V and V star. Okay, so yeah, note that X is 5-dimensional, right? It is a subset in 6-dimensional space subject to linear, to the relation V star of V is 0. We have two projections onto 3-dimensional space, so the fibers of each of the projection is 2-dimensional. And now we shall define the Fourier transforms on the space X. That's what we call Fourier transforms, corresponding to simple reflections in the Weil group. We have, this is a group of rank 2, so there exist two simple reflections as Fourier transforms along the fibers of this projection. So precisely for any vector V, and for any vector V, say, there is a canonical form on the fiber in X or over the vector V, which consists basically on all the covectors whose value of V is 0. We denote it by V perp. I will not write a formula, but it can be, it's very transparent how to write this. So this gives these two top forms on the two-dimensional spaces, give associated measures. And we define the operators phi1 and phi2, which is associated to simple reflections, using the Fourier transforms along those two-dimensional fiber. So you can stare on this formula, you can see how symmetric it is, and just to appreciate that, in fact, we are talking about the Fourier transform along the two-dimensional spaces. Okay, so this is quite easy to see that these operators are unitary and each of them is involution. And now, in order to show that these operators indeed give us action of the Weil group, we must check so-called braid relations. So, because the S1 and S2 generate the Weil group modulo braid relations. So these braid relations are of the form, the unique braid relation for SL3 is just S1, S2, S1 is S2, S1, S2. So that's what we must show for this particular case. So let me sketch the proof. The idea would be to consider a dense subspace of functions inside the L2 space. It satisfies several properties. So first of all, we consider the space of U psi equivariance. Here, U, I remind you, the unipotent radical, and psi is this time a non-degenerate character of this radical. So there is a projection space from S0 of X to its equivariant. We construct space such that the kernel doesn't contain G subrepresentations. And in fact, this space of coinvariance can be identified with a space of functions on T, because we are looking at the kind of functions on G, which are U invariant on one side and U psi invariant on the other side. So must be supported on the maximal Brouwer cell. It's just a sketch. If you don't follow, it doesn't matter much. But the idea that the operators phi1 and phi2 both preserve the space, and hence they give rise to the operators on coinvariance. And on this coinvariance, the action is just geometric, geometric through action of T. So in this case, by definition, there is a equality of the reduced operators as operators on T, and because of the first property, and because the operators phi1, phi2, phi1 are in fact, their images as in fact G representations, from this follows the braid relation. Okay, so this this kind of proof has nothing to do with the specific case of SL3, and actually works for arbitrary split group. Okay, so so far about split groups now. So now I'll present, yeah, and basically all this construction has been done, sorry, in 80s by Gelfand and Gruev. So now I'm coming to the contents of the our work, the question was how to generalize the same construction for a quasi-split group. So what is quasi-split group? Quasi-split group is also reductive group defined over a field which admits a Borel subgroup but with the decomposition of its radical and the torus, but the torus is not necessarily a split one. Okay, so the typical example of a quasi-split group which is not split is a unitary group. And another example is orthogonal group, which is corresponding to a quadratic space with a quadratic form, which is not split, meaning not sum of the hyperplanes. Okay, so in any case, we consider a quasi-split group G, and it contains a maximal torus, and with respect to this torus, there is a relative root system. And now, exactly as the group, the split group can be kind of glued from many rank 1 subgroups, which are all equivalent, which are all isomorphic to SL2. For a quasi-split group, there might be 2 possible rank 1 groups. One of them is SL2 and another is SU3. So the group of automorphism preserving a Hermitian form on a 3-dimensional Hermitian space. Okay, so the Weil group, as before, is generated by simple reflection, where every simple reflection corresponds to a non-divisible relative root in R. Okay, so before we said that if our group of rank 2, if our group of rank 1 is just SL2, then the operator corresponding to this simple reflection is defined using the 2-dimensional Fourier transform. And it will be just the same in the quasi-split group. But the question is, what happens when this group of rank 1 has is the unitary group? Okay, how to define it? And here a new idea was needed, and to define it, we use the point of view involving minimal representations. And now I, for a minute, go back to the SL2 case. The Fourier transform in the case, now I'm looking at the V here is a 2-dimensional space. The Fourier transform looks like a distinguished operator, but in fact it belongs to a family of operators on L2 of V. And let me present the setting. Okay. I look at V as being a 2-dimensional symplectic space. And let me also consider a quadratic space H, also of dimension 2. So their product has a natural structure of 4-dimensional symplectic space, in which case there is a natural embedding of the symplectic group SPV times orthogonal group of H into the symplectic group of their tensor product. Okay, this is symplectic group SP4, basically. And even there is a splitting into the double cover of such a group. Okay, so why double cover matters? Because the double cover of SP4 admits a very special minimal representation called Weil representations. And this representation is realized on the space L2V such that the SPV, which is basically also SLV, SL2 times SO2 acts in a geometric way. This is a familiar formula which we introduced in the very beginning. And in addition, the involution in the orthogonal group, which is not in the special orthogonal group, so acts by the Fourier transform. So these are just properties of the minimal representation. And in this way, we actually see that since symplectic group is just SL2 and orthogonal group is just torus, which is a multiplicative group, semi-direct product with W, we get naturally from the minimal representation on SP4, which has not appeared at all before, by restriction of this representation, we get a natural extension of the action of G times T to G times T times W. Okay, so this is so there is nothing new here, but it gives just a different point of view how this Fourier transform might appear. Now we can apply kind of the same strategy for the group SU3. Okay, we also play the game of small dimensions. In this case, the group SU3, of course, has behind it some quadratic extension. Okay, the Weil group contains two elements, so we just must find just one operator. Okay, so in this case, we start with a Hermitian space of dimension 3 and over K, composing it with the form, with Hermitian form, with the trace. It can be also considered as just a quadratic space over F of dimension 6. Okay, in this case, G mod U has again a very easy model as just a set of vectors in W on which the form is 0. So it is a cone of non-zero isotropic vectors. And as I said, naturally SU3 lives inside O6 because whatever preserves the Hermitian form also preserves the corresponding quadratic form. And there is a natural embedding of O6 times O2 inside O8. And here is a lucky miracle that the minimal representations of O8, this is a very special representation, can be realized on the space L2 of X. And the action of SU3 is geometric, together with the action of the multiplicative group. So if you want to look for the unitary involution, which commutes at least with the group SU3, and anti-commutes with this one-dimensional, with this group of multiplicative group, we're better take an element inside O2, which is not, which is an involution and is not contained in SO2. Okay, so in this case, in this sense, this is a construction which is quite similar to the previous one. Okay,
Nadia,
and it actually, yes.
We have to finish in about 2 minutes.
Yes, definitely. I have just one slide about final remarks. Okay, so I just explain here how, using this point of view, we can guess the candidate for the operators S alpha. Now let me just say some final remarks. So first of all, to guess is very fine, but then we have to compute it explicitly. And it has not very intuitive form, unlike the usual Fourier transform. Okay, but the formula uses Radon transform. unfortunately, I don't have time to explain how it arises. Okay, now you might think that this construction is very arbitrary. So we used some small dimensions. So how do we know that our choice for phi of S alpha was the right one? But then the nice compatibility criterion is that when the quadratic algebra for our form is split, in which case SU3 is just exactly SL3, it is possible to check that the operators defined one theta correspondence, phi S alpha, is actually the same as phi1, phi2, phi1, which was defined for SL3. So this shows the compatibility. The braid relations in the quasi-split group are just proven the similar way to the split group, and this is still in progress. And the other remarks concern about so here basically I finish. Just let me just mention that one of the possible applications of defining these operators FW generally is that they give rise to normalized intertwining operations between pi of chi and pi of w chi, which are canonical. A priori, they are defined only up to constant, and lots of work has been done to define the good normalization of it, but this choice defines them canonically. Okay, so and the last thing, as I already mentioned, that for split groups, the result has been proven by Gelfand and Grave, but we do it for a quasi-split group. Thank you very much for your attention.
Thank you very much, Nadia. I will unmute you to applause if you want. We will reconvene with our next talk in 5 minutes precisely. If you want to ask questions, you're welcome, but this is also the break because we're a bit over time. So, so both break and questions, so you can speak, and we'll reconvene in 5 minutes.
Hi, Nadia.
Yes.
May I ask regarding the canonical construction, do you have a functional equation, or maybe I missed
it? Yes, of course there is a functional equation. Since, say, let me go to the beginning here. Since we have the phi W1 times phi W2 is phi W1 W2. When you reduce it, decompose that, so each operator's FW gives rise to the operator from pi of chi to pi of WK, and of course there is a functional equation.
So do you compute those normalization constants, or?
No, I don't compute them. I just I defined FW kind of, we defined it before taking spectral expansion along action of the torus, right? So the correct normalization just pops out of that.
Okay, so our second speaker is Alexei Antin from Tel Aviv University, and he will talk about the minimal ramification problem in inverse Galois theory.
Okay, good afternoon, everybody. I thank the organizers for the opportunity to speak here. I'm going to talk about joint work with Arno Feim from Dresden and Leo Soroka from Tel Aviv University. I'm going to talk about the minimal ramification problem in inverse Galois theory. So to set things up, let's start with a very famous and classical problem, the inverse Galois problem, which can be stated over any global field. A global field is either a number field or a function field over a finite base field. So let K be a global field and G some finite group. And it's natural to wonder if there exists a Galois extension L of K with Galois group G. If the answer is positive, we'll say that G can be realized over K. And the folklore conjecture going back to the 19th century, I guess, is that indeed for any global field K and finite group G, this is possible. We can find an extension with Galois group exactly G. And in general, it's open even for the case of the rational numbers and the rational function field over FQ. And this is one of the most famous open problems in arithmetic geometry. And let's quickly recall what is known over Q. So K will be Q here. The abelian case is basically cyclotomic extensions, very simple. The case of the symmetric and alternating groups, which I denote by Sn and An, was worked out by Hilbert in 1892. The solvable case was finally solved by Shafarevich after a couple of incomplete attempts in 1989. And many groups of Lie type, but far from all, were realized by various methods, by several authors, which I didn't even list all of them, long series of results, and all sporadic finite simple groups except M23, the Mathieu group, had been realized over Q as well. All of them based on the method of rigidity, which I won't go into. Many other interesting groups have been realized over Q, but the general problem is far from settled. Okay, so this is just the basic inverse Galois problem.
So what families of simple groups are not known?
Well, even something like PSL2 is not known in general. It's known with some assumptions on the field.
Yeah.
Okay, so a lot of them are not known in general. Usually there's some arithmetic condition on the parameter of the group. Okay. So, okay, that was the basic inverse Galois problem, and now we want to make it even more difficult. So when faced with a hopelessly difficult problem, what we do usually is find an even harder one, then try to work out some interesting new special cases. Okay, so now K will be a number field and G a finite group. And assuming that G can be realized over K, what would be the realization that has the minimal number of places of K that ramify in the extension L over K? So we denote by RKG the minimum of the number of ramified places in a realization of G. And so PK denotes the set of places of K, including infinite places that are ramified in the extension. I guess, yeah, sorry. Yeah, okay. And we define RKG to be infinity. If G cannot be realized, then we conjecture this never happens. Okay, so now, okay, we want to first formulate a conjecture on what RK of G may be. And we denote by D of G the minimal number of elements that generate a group G. And the conjecture was stated by Boston and Markin, saying that RK, sorry, what I wanted to write is RQ of G. So there's a typo there. So the minimal number of ramified places in a realization of G would be the maximum between 1 and the number of generators of the abelianization of G, provided G is not trivial. In particular, this implies the inverse Galois problem, but yeah, this is a stronger conjecture. And the lower bound here is easy to deduce from class field theory. So this what gives This how this expression was guessed is by having this lower bound and conjecturing that it is also attainable. Okay, so in particular, in the case of the symmetric and alternating groups, this predicts that there's a realization with a single ramified place for n at least 3, and even this case is still wide open. Okay, so the inverse Galois problem is solved for these groups in the 19th century, but if we add the minimal ramification condition, it's still open. Okay, so there are some known cases. So the conjecture holds in each of the following cases. First of all, G abelian. This is just an easy conclusion from class field theory, again, cyclotomic extensions. All groups of order up to 32 were worked out by Boston and Markin as evidence for their conjecture. G semi-abelian P group was worked out by Kisilevsky, Neftin, and Son. Some other solvable groups were worked out by Plans, Markin, Ulam, and Kisilevsky, Son, but far from all solvable cases. So the general solvable case is still wide open. And a nice result by Barry, Soroka, and Schlank is that RQ of Sn is at most 4 for all n. And they proved it using the Green-Tao-Ziegler theorem on the solvability of linear systems of equations in primes. So very nice tool used here, but it only attains 4 ramified places and not 1 as predicted by the conjecture. And it is not a similar uniform bound for all n is not known for the alternating group at the moment. Although in principle, the method of Barry, Sorokin, and Schlank should be able to produce such a bound. The question is how to minimize it, but we won't go into it right now. So some further evidence for the conjecture in the case of Sn. This is just evidence, not a proof. At this point, so first I recall Schinzel's hypothesis H, which predicts that for k reducible polynomials over Z, assuming there are no local obstructions, so we can always find a value of n such that all fi of n are prime. Also, very famous and difficult conjecture in classical number theory. And assuming this conjecture, we can show that indeed RQ of Sn equals 1. And since this conjecture is widely believed, this gives evidence to the Boston-Markin conjecture in this case. Okay, so I'll briefly sketch the idea of proof here. So what we do is we take some monic polynomial of degree n and consider the Galois group of polynomials of the form f of x minus a, where a is some integer. Okay, so this would be some subgroup of Sn with the action on the roots of the polynomial. And for most f and a, the Galois group is actually Sn. So this is a quantitative version of Hilbert's reducibility theorem. And if we assume that also f of x minus a has n real roots, and additionally the discriminant of f of x minus t, a parameter here, so the discriminant in x is some polynomial in t. If we assume it's irreducible, then Schinzel's hypothesis says that there would be many values of a such that d of a would be prime. And this would be the only prime ramifying in the splitting field of f of x minus a. The prime at infinity would not ramify because of our assumption on the real roots. Yeah, so this would give us what we want, but we need to find an a such that d of a is prime. And indeed, even this argument is incomplete because d of t is actually a constant multiple of an irreducible polynomial. And the divisors of this constant multiple need to be handled as well. So the full argument is actually quite technical, and it makes use of our function field results, which I'll talk about next. But in any case, this whole argument assumes Schinzel's hypothesis H, otherwise it doesn't work. Okay, but it gives evidence for why it's reasonable to expect RQ of Sn to be 1. Okay, so now let's move on to the function field analog of this problem, on which we have in fact obtained the strong unconditional results. Let P be some prime, Q a power of P, and K for now a global function field with field of constants Fq. And the main example eventually will be Fq of T, which is kind of the parallel of the rational numbers in the function field world. We define Rk of G again to be the minimum of the number of ramified places, but we don't consider all extensions with Galois group G. We only allow geometric extensions, which means that the field of constants remains Fq. The reason we make this restriction is because if we allow extending the field of constants, there are many extensions that are unramified everywhere. So this would not parallel the Boston-Martin conjecture, and the correct analog of the problem is restricting to geometric extension. Okay, so this is the reason for this definition. And we denote by P of G the group generated by the P-silo subgroups of G. We need this notion to state our conjecture. Now the main conjecture, the analog of the Boston-Martin conjecture, is that the minimal ramification number for G is the maximum of 1, and the number of generators for the abelian part of G modulo its P part. Yes, so we need to eliminate the P part because well, even in the abelian case, we can have a P part with huge rank, which can be obtained with just ramification at a single place. This is a phenomenon related to characteristic P, obviously. But in the special cases of Sn and An, we just get the same conjecture as over Q. Okay, so the conjecture, we can realize Sn and An with one ramified prime. Okay, so let's see what we can prove in this case. So the abelian case, well, first of all, the lower bound is correct. Yes, so we do obtain the lower bound for any group G. This is, and for abelian group, we obtain the precise conjecture. And just like in the case of K equals Q, this is deduced from class field theory. So nothing too complicated here. A few technical arguments, but nothing deep. Now the more interesting results are the results for the symmetric and alternating groups. So for the symmetric groups, first of all, we showed that we can always realize the Sn with at most 2 ramified primes, which is almost what we want. The conjecture predicts 1. And compare this with what is known over Q, which is just 4. Now, if we assume additionally that either the characteristic is 2 or the characteristic is at least P, but is at most N, but not N minus 1, or we assume the remaining case, but a small restriction on Q, it has to be 1 mod 4. In each of these, or if we assume Schinzel's hypothesis H, so this is the conditional result. So we just need to assume one of these, not all of these, just one. So in each of these cases, we get the full conjecture for Sn. So we almost settle it completely in the function field case, except we have, if P is bigger than N, we have this Q equals 1 mod 4 restriction. And eventually we hope to eliminate this as well and get the full result, but as you can see, this is almost the full conjecture. Okay, so these are the results for Sn. Now let's move on to An. Again, we can show, well, this time we require the characteristic not to be 2, but then we show that 2 ramified primes are always enough. And nothing like this is known over Q at the moment with any fixed bound. And moreover, if we assume one of the following, so either P equals 2 and the small restriction on n mod 8, or P is between 1 and n minus 1, or P equals n, or P equals n minus 1 and FQ contains FP squared, or n is at least 13, and here we do need to assume an analog of Schinzel's hypothesis H. So in under either of these assumptions, we get the conjecture, the realization with one ramified prime. And I should remark that, in fact, the method gives many other unconditional cases, but the conditions on P and N are a bit complicated to state, so I will omit them. So the results for AN are weaker than the results for SN at the moment, but as you can see, quite close to the full conjecture as well. Okay. So in the remaining time, I will talk a bit about the methods. And in fact, for this problem, the methods are even more interesting than the problem. I would have to say the main motivation, at least for me, for studying this problem is that various different tools from different areas can be applied to this problem, which is what makes it a very good problem to attack. So K will be the rational function field over FQ to the power of P. There are two fundamentally different cases, as you could have guessed from the previous statements. There's the case of a P bigger than N. So this means our extensions have to be tamely ramified. And there's the case of N at least P. In this case, extensions with Galois group AN or SN may be widely ramified, and this is quite useful, and we obtain stronger results using wild ramification. Okay, so all of our results are explicit, more or less. We obtain explicit polynomials with Galois group Sn or An in each case. So let's start with our first construction, which is valid for P bigger than N. This uses results on twin primes over function fields. So for simplicity, I'll only mention Sn, but the same method applies to An with some modifications. So let's denote by U a new variable. And one can find a geometric extension N over FQU, which is ramified only over 0, 1, and infinity with Galois group Sn. So this is essentially a construction due to Hilbert, only considered in characteristic P, but it still works as long as P is bigger than N. Okay, and now what we do, we take a base change, so we replace U with H of T, where H is some polynomial, so there's a typo, H is not a rational function, it's a polynomial in this construction, and we form the base change, so FQ of U is embedded in FQ of T, via taking U equals H of T, and now we take the compositum of M and FQ of T, and we obtain an extension L of FQ of T. And by Hilbert's irreducibility theorem, this extension will typically also have Galois group Sn. And here we actually use a recent quantitative version of Hilbert irreducibility. Well, because we need a precise quantitative form in our argument. So we get an Sn extension, but where is it ramified? It will be ramified over H and H minus 1 and possibly infinity. Okay, so when we base change this 0, 1, and infinity, we get this new ramification locus. And if n divides the degree of H, then actually the ramification at infinity disappears. So this is known as Abjankar's lemma. And we are left with the divisors of h and h minus 1. So what we want to get just 2 ramified primes is to make sure that h and h minus 1 are irreducible and the degree of h is divisible by n. And here we use a relatively recent result that says that for large enough finite field FQ, Q at least 59, there are quite a few irreducible polynomials h such that h minus 1 is also irreducible. So this is a version of the twin primes conjecture over function fields, a quantitative version, and it's based on the Maynard-Tau-Sieve method. And using this and the previous arguments, we conclude that we can realize Sn with at most 2 ramified primes, namely h and h minus 1 for a q large enough, but for q up to 59 and n smaller than p, this is just finitely many cases, and we can use a computer search to find the necessary twin primes satisfying all the other conditions. So we obtain the full result. The full result, I mean, showing that we can do this with 2 ramified primes in all cases. This doesn't quite give us 1 ramified prime. So for this, we will need to use different constructions. Okay, so let me now move on to the second construction for p bigger than n. This is a somewhat different idea, which instead of the Maynard-Tau method uses different heavy artillery, probably even heavier artillery in the form of the classification of finite simple groups and its corollaries. So we consider now the splitting field of a polynomial of the form f of x minus c of x u. So somewhat similar to our previous construction. And now we know that m is ramified over the critical values of the rational function f over c. Okay, so this is a simple exercise to see this. Now, and the Galois group of m over fq is closely related to the monodromy group of the rational function f divided by c. Essentially, this monodromy group under some conditions. And now we use a very deep result, the classification of monodromy of rational functions, which was completed in recent years by Ziv and Wang, following previous work by a series of authors. And this classification heavily uses the classification of finite simple groups. So it's a very deep result in group theory, essentially. And under the additional assumption that f prime c minus fc prime is irreducible, what this means is that the critical values of the rational function basically all fall under one Galois orbit, so they form just one ramified prime, except for the prime at infinity. And the classification of monodromy implies, in this case, that the Galois group is indeed the same. But there's no direct way that we know of to prove this without using this deep classification. Okay, so now we apply base change as in the first construction to obtain an extension ramified only over the divisors of f of h. So f is the only finite prime which is ramified in the extension m. And now assuming either hypothesis H or unconditionally assuming Q equals 1 mod 4. So this is actually a case of Schinzel's hypothesis that we can prove, assuming that K is n minus 2. We can find H of suitable degree such that f of H remains prime, and thus we obtain an extension with just one ramified prime in Galois group Sn. Okay, so to conclude, in this case, the main tool is this deep classification result of monodromy of rational functions. Okay, so this is our main tool for this construction. And it works under some restrictions on Q, as you can see, and hopefully can be generalized in the future. And I will finish with the final construction, which is closely related to a famous result called Abjankar's conjecture, which was stated as a conjecture in 57, but proved by Renault, generalized by Harbaiter in the 90s, which says that if G is a finite group, well, this is a special case of the conjecture, it says that if G is a finite group, which is its own P of G, i.e. generated by its P-style of subgroups, then there exists an extension over Fp bar of T, right? Note that this is not a result over Fp, it's a result over Fp bar, ramified only over infinity with Galois group G. Okay. And the proof is not, doesn't give an explicit extension for every group, but in a series of papers, Abjankar and some collaborators actually wrote down explicit constructions for Sn, An, and many classical groups and some sporadic groups. These examples led him to the following conjecture. So this is still wide open. The conjecture says that if G is an extension of a cyclic group by a group satisfying H equals P of H, then G can be realized over Fpt with ramification only over infinity. So this is very similar to Abjankar's conjecture over Fp bar, except we remove the bar. Okay, so this is a conjecture over Fp, and this is a much more difficult conjecture probably than the original one. Still wide open. And in the case An, these extensions would have to be geometric. This is a simple exercise, and we get actually also a solution to the minimal ramification problem, provided we can settle this conjecture for An. And indeed, we do settle this conjecture for An in some cases, at least. So if either P is 2 and the small restriction on N mod 8 holds, or a P is between 2 and N minus 1, or P equals N, or P is N minus 1 and Fq contains Fp squared. So in all of these cases, we can prove Abjankar's arithmetic conjecture for An, and as a corollary, obtain the conjecture on minimal ramification for An. So the case N greater or equal to P, we get even stronger results than the other case. And to obtain this result, we generalize Abjankar's constructions. And okay, I stated this for An, but the ideas can be applied to get minimal ramification for Sn as well. Okay, so with this, I finish.
Thank you very much. I will unmute everyone so we can applause. Thank you. Questions?
Yeah.
Hi, so can I ask?
Yeah, I do hear you.
Can you hear me?
Yes. Yeah, I did hear you.
Sorry. Okay. Okay, good. Sorry. Good that you can hear me. Okay, can you go back to the monogery classification? I had the feeling that I know this result, but I can't recognize it.
You definitely know it. Even more general results, I guess.
So I'm not sure what's the, like, is it, do you assume that it's tame?
Well, in this construction, yes, we only need the tame case. Yeah, yeah, exactly. So we're not using the wild case, which is more complicated. This only involves the tame case. As you can see, P is greater than N here. So yeah, we only use the tame case.
So it's actually like over FQ bar, and then you just look what what is defined, right?
Yeah, then you need to do some work to make sure that transition from FQ bar to FQ works, but yeah, okay, we did that work and it works.
I see, but okay, so it's the same classification of algebraically closed fields when you're
yeah, exactly. It's the classification over C, basically, that's what we're using.
Okay, so now I recognize it a bit more. And also, could you say something about the difference between that and Q, like like doing AN over FQ of T and doing it over Q? Like, what would you need over Q to get it?
Well, I would need the derivatives of integers, and I would need the monodromies of rational numbers. So both notions don't exist at the moment.
Yeah, okay. No, thanks. It's heavy sold. Okay.
Which is unfortunate. Either that or use Schinzel's hypothesis H, which is also open at the moment.
Wait, you can use just Schinzel to get at most 2, right?
No, in fact, so for the case of Sn, let's see. Okay, so for the case of Sn, we actually obtained 1 under Schinzel's hypothesis H, and for the case of An, we didn't do it yet, but it in principle may be possible as well.
Okay, no, that's interesting, thanks.
Okay, if no more questions, then let us thank our speaker once more. So we will reconvene in 5 minutes. So next talk is in 3:35. Thank you very much. Okay. You can also ask questions while we set up the next speaker. Okay. Alexei, could you please stop the sharing, please? Thank you. Okay.
So you scale the argument of the function. For instance, take the most simple infinite dimensional algebra. Let's say the polynomial ring in one variable. If you consider these two subspaces, it's relatively easy to see that indeed there are two generating subspaces for A. The growth function of the first one will be n+1, and of the second one will be 2 times n+1, but still they're both linear. And this is really the equivalence class of this asymptotic equivalence relation. Now, and this is really the definition of growth rate. When we want to study the growth rate of an algebra, of finitely generated algebra, we really mean this function, this dimension sequence, relative to some arbitrary generating subspace, but considered only up to this equivalence relation, which we denote tilde. So this is tilde. Yeah. And therefore the growth rate is really an invariant of the algebra. So growth functions can be quite diverse. They can be either a polynomial bounded, in which case we can consider the degree of this polynomial. It is called the GK dimension or the Gelfand-Kirillov dimension. For instance, the growth rate can be something like n cubed times log n square. And in this case, the degree of the polynomial part will be 3. They can be exponential, meaning that lim sup of the nth root of gamma of n is larger than 1, and they can be intermediate, which essentially means anything in between. I'll briefly go over some interesting appearances of growth of infinite dimensional algebras in real life mathematics. So you'll believe me that it is worthy to listen to the rest of the talk. So let's begin with commutative algebra. If we have an affine scheme of finite type, then the growth of its ring of global sections is just symptotically n to the dimension of x. Or in language of commutative algebra, it just means that the GK dimension of finitely generated commutative algebra is just equal to the cool dimension, which is defined in terms of chains of prime ideals. Growth is plays a crucial role in non-commutative geometry as well. There's a notion of a non-commutative projective scheme, which I don't want to get into, but basically what you do is to construct some kind of a non-commutative projective scheme upon some given non-commutative graded, well-behaved ring. And what happens is that the dimension of this non-commutative scheme, whatever it is equal to the GK dimension of A minus 1, which is a perfect analog of what would happen in the commutative case. Infinite dimensional rings with important growth conditions appear also in the theory of differential operators of algebraic varieties. For instance, in the theory of D modules, right? Holonomicity is defined by exactly having critical growth rate, having the least possible growth rate. There are also connections with Galois theory. It turns out that you can bound a number of Galois extensions of a function field with given Galois group in terms of functions of the discriminant with some bound arising from the growth rate of some non-commutative infinite dimensional graded algebra. This is Male's work. I'll get into Lie algebras a little bit later, but I just have to mention it now. There's a tight connection between the Lie algebra, the growth of the Lie algebra, and the growth of its universal enveloping algebra. I'll review it deeper in the next part. There's also a tight connection with growth of groups. If you take a finitely generated group, then you consider an infinite finitely generated group, you can consider its a Cayley graph with respect to some fixed symmetric generating subset, and measuring the magnitude of the n balls in this Cayley graph is just in one-to-one correspondence with basis elements of the nth power of the generating subspace of the group algebra. So studying growth of groups is equivalent to studying the growth of their group algebras. They're just the same functions. And the last appearance I want to mention, because I will use it later and it will play a key role in our construction later, is symbolic dynamics. So it turns out that out of a closed subshift over some finite alphabet, you can construct so-called monomial algebra. I don't want to get into the definition now, but this is a certain non-commutative algebra, which turns out to encode and to reflect in its algebraic nature many interesting dynamical properties of the subshift you started with. So this is some kind of a way to transfer data from symbolic dynamics into non-commutative algebra. And we'll see this in action in a few slides. So after this motivation, I hope we're now motivated to understand how do growth functions look like? Or in other words, which functions are growth functions of algebras? So there are two evidently necessary conditions satisfied by any growth function of a finitely generated algebra. So the first is being increasing, and well, this is satisfied as long as your algebra is infinite dimensional, because otherwise you get stuck at some finite level and your dimension is finite. And the second is being submultiplicative in the sense that is written here. And this is also not hard to see. The reason is that in the tensor algebra, you can decompose any length n plus m monomial into its length n prefix and length m suffix. So these are two very easy necessary conditions. And now one can ask if they're also sufficient. Is it true that any function that is increasing and submultiplicative is in fact equivalent to the growth function of some finitely generated algebra? And the first major step towards understanding how huge is the space of growth functions of algebras, I think, was this construction of Bertoldi and Smoktonovich, who proved that any reasonable function in this sense, well, increasing and somewhat duplicative, is almost realizable as growth function of an algebra. What does it mean, almost? You have this a polynomial error factor. Up to this error factor, your desired function, as long as it is indeed increasing and somewhat duplicative, is equivalent to growth function of some finitely generated algebra. And in fact, if you impose the further regularity assumption that your function is equivalent, asymptotically equivalent to a polynomial factor of itself, meaning that it is somehow a uniformly super polynomial, then this function is actually precisely equivalent to the growth function of some finitely generated algebra. I'll just mention that this condition, what it means in first order language, is that there exists some constant such that f of c times n is larger than n times fn. And if you think of it, any sufficiently regular function that it is more rapid than n to the log n satisfies this condition. And I want to mention just in one sentence that there have been interesting examples and exotic constructions by Trofimov, Belov-Borisенko, Latishev, and others who produced examples of oscillating growth functions. These are functions, growth functions that oscillate between polynomial, in fact, the least possible degree polynomial, and any sub-exponential function. So they're infinitely often very slow and infinitely often very rapid. And this phenomenon, this weird phenomenon, cannot happen, for example, within the class of growth functions of groups. So this is some kind of a weird phenomenon that happens here. Okay, I want to briefly sketch for you the idea behind the construction of Bertoldi and Smoktonovich, because we're going to take it further steps, a few steps further. What they did is to start with some finite alphabet and construct some kind of a generalized infinite tree. It's actually a collection of uncountably many infinite words, which can be thought of as geodesic arrays in some infinite tree. So I'll tell you how they do it. They start with the finite alphabet, and then they pick some finite subset, some subset of this alphabet, and consider all concatenations of a letter from the alphabet and from this subset. Then they choose some subset of this new set and put it here. So this is of length 1, this is of length 1, this is of length 2, where C2 is just a subset of this set, and so on. And so on. And this way they construct uncountably many infinite words that out of which they're able to define a suitable monomial algebra. And the point is that finite paths in this generalized tree correspond to non-zero monomials in this algebra. And therefore they're able to control the growth of the resulting algebra. Of course, the main challenge here is to show that you can choose your system of sets in such a way that indeed you will realize the desired function as growth function of this algebra. And they left open the following question, which is the answer is very interesting because of different applications. They left open whether this resulting algebra can in fact be modified to be prime. So prime algebra, just recall that it means that the product of any two non-zero ideals is again non-zero. And prime ideals and prime algebras are very important from various perspectives, but in particular in the context of monomial algebras, it turns out that, and it is actually very easy to see, prime monomial algebras are defined in a certain sense by a single by infinite word over the same finite alphabet. And this will play a major role in the sequel, because we're going to actually consider some subshift generated by this by infinite word and proceed from there to symbolic dynamics and groupoids and some other interesting objects. So the answer to this question is yes, we're able to answer this in the affirmative. And the idea is, so this is a very high-level proof sketch, but the idea is to take this system and then modify it in such a way that you actually insert infinitely many copies of each finite path so that you obtain what we call a recurrent system, meaning that every factor appears infinitely many times. But again, the main challenge is to make sure that you don't blow up the growth rate, and it's not enough to put those copies sparsely enough, because well, it might be that you generate this way too many new words, so you have to be very careful. But again, this is it is possible, and as I mentioned, the algebra or resulting from this modification is actually defined by a single by infinite word over our alphabet, finite alphabet. Just as a side application, I want to mention that even this modification enable us to answer or to re-answer an old question of George Bergman. He asked whether the Krull dimension, which is just a classical Krull dimension, the length of chain of prime ideals in an arbitrary finitely generated algebra, is always bounded above by its GK dimension. So as I said, for commutative algebras, there's just equality. And for many other classes of algebras, it is known that this inequality holds, including Noetherian algebras and rings satisfying polynomial identities. But in general, the answer is no. And the first proof that the answer is no was given by Bell in 2005. However, there is no any concrete counterexample, because he uses some non-constructive methods, some Zorn's lemma. So you don't really have any tangible algebra which you can, for example, compute its precise growth rate. And we were able to derive the first constructive counterexample. In particular, it is a monomial, it is graded. You can write an algorithm, you can algorithmically produce all the elements in this algebra, and you can effectively bound its growth rate. And it is sharp from several points of view, which I don't want to get into. So this is just some kind of a side byproduct. I want to proceed to infinite dimensional Lie algebras and tie these things together. So in the very same manner that you define growth for finitely generated associative algebras, you can actually define growth for finitely generated Lie algebras by replacing your generating subspace with a Lie generating subspace, and considering, instead of the dimension sequence of powers, just the Lie bracket powers of your generating subspace. Again, this function is increasing, it is exponentially bounded, and it turns out that there's a tight connection between the growth of your Lie algebra, the original Lie algebra, and the growth of its universal enveloping algebra. So this is somehow similar to the connection between groups and group algebras. Again, you have some kind of a left adjoint construction, and you want to understand how the growth reflects in this construction. So if the dimension of your original Lie algebra is finite, then the enveloping algebra will be infinite dimensional, but of polynomial growth. And the degree of polynomial will be exactly the dimension of the Lie algebra. And this is essentially the Poincaré-Belkov-Witt theorem. Now, what is more interesting is that if your Lie algebra is infinite dimensional, but of sub-exponential growth, then the enveloping algebra will also have intermediate growth. It will always be super polynomial, but also sub-exponential. And this observation is a beautiful combinatorial observation made by March Smith in '76, even before groups of intermediate growth were known. Actually, further calculations by Victor Petrogradsky enabled to really compute the precise behavior of this of the growth function of the enveloping algebra in terms of the growth of the original Lie algebra. So, for example, if you start from a Lie algebra with polynomial growth with some a degree alpha, then the enveloping algebra will have this kind of sub-exponential growth, which is exponent of n to some power between 0 and 1. So this is indeed a sub-exponential, and so on. But what Petrogradsky really did is much more impressive. He actually unified, he invented a theory of infinitely many dimensions for algebras, for the algebras, for associative algebras, which unifies and generalizes some known and extensively studied dimensions. And the most important thing is this formula, that passing from a Lie algebra to its universal enveloping algebra translates to passing one level higher in the dimension. So you have, imagine that you have a hierarchy of dimensions, 1, 2, 3, etc. And the dimension, the value of the dimension remains the same, but you just pass to one level higher. So his dimensions, I don't want to define his dimensions because it's quite technical, but they are based upon families of functions. These are the families. And I want you to look on the right column, because these are the dimensions, the first, second, third, and the fourth, and so on dimensions. So the first dimension is just the vector space dimension that we all know of. The second is the GK dimension, which I mentioned to you before. The third is the GK super dimension, or slight modification of it, which I didn't define to you, but believe me that it exists, and so on. So this is like a system of dimensions that enables you to exactly bound the growth or describe the growth of the enveloping algebra of a given Lie algebra. Petrogradsky also posed two open questions, which are very natural when you define such a wonderful system of dimensions. The first is the following. I call it the coverage question, because he asked, so you have this sequence of dimensions, and he asked if it is possible that there's some Lie algebra that falls in between two levels. So maybe its Q dimension assumes 0, but the Q plus 1 level assumes infinity, but the Q plus 1 level assumes 0. So the dimension is not caught by any of these dimensions. And if the answer was negative, if any algebra would have a minimal layer in which it has positive dimension, that would mean that that would be wonderful from the point of view of classifying, right? We could start by classifying the simple Lie algebras with minimal dimensions and proceed from this point. And the second question, which is not less natural, is the flexibility question. So you have an infinite sequence of dimensions. You want to know whether, well, which values are actually possible. For example, the first dimension, right, the vector space dimension, only integer values, positive integer values are possible. The GK dimension, you cannot have values between 0 and 1, and it gets more and more complicated. So, and now I want to state the main construction, the main result of this part of the talk. It relates to simple Lie algebras, but in fact, and as just one byproduct of it, we're able to answer these two questions in full generality. Unfortunately, in the pessimistic answer. So here is the result. For any increasing and some multiplicative function which satisfies this additional uniform regularity condition that we met before, there exists a finally generated even simple Lie algebra which realizes this function as its growth function. In particular, we were able to show that for all layers, for every 2 layers, there exist Lie algebras which fall in between these dimensions, except for the the first, right, where it is known to be possible, the first two steps. And also we're able to show that any non-negative real number is actually a value for these dimensions, starting from the first point where it was not known. And in particular, I think it demonstrates, again, the diversity and how huge is the space of growth functions, even of simple Lie algebras. I just mentioned that simple groups of intermediate growth were only recently constructed by Nekrashevich. It's a very deep construction. So, okay, I want to mention in this context that simple Lie algebra, graded simple Lie algebras of polynomial growth were classified. This is what this was known as Katz's conjecture. It was finally resolved by Mathieu. So Mathieu classified Z-graded simple Lie algebras of polynomial growth. And I want to mention that our algebras are also Z-graded. They're simple, and we can also modify them to have a arbitrary polynomial growth. But don't worry, this is not a contradiction to Mathieu's classification, because of a very delicate point, which is, of course, crucial. And the point is that Mathieu's classification is for graded algebras with finite dimensional homogeneous components, whereas our grading is very natural, but the homogeneous components turn out to be infinite dimensional. So the algebra is finitely generated but the homogeneous components are somehow infinite dimensional. Okay, I want to take you into the sketch of the multi-domain journey that leads to this construction, and it involves various fields.
So you have 3 minutes for the journey.
Yep. We start with trees of infinite words as in Bartoldi-Smoktonovich construction. As you remember, I said that we are able to modify them to result in trees that give rise to prime algebras. And as I said, prime algebras are actually defined by infinite words. Now, the next step you have to do is to make sure that these infinite words are not only recurrent, they're also uniformly recurrent, which is well, it means that every factor appears in bounded gaps. And this is a very technical and very not easy modification. But after you do this combinatorial modification, you can consider the minimal subshift generated by infinite word, which is just the closure of the orbit, the shift orbit of this infinite word. And it is known that since your word is uniformly recurrent, you have a minimal subshift, out of which you can construct what is called Ital groupoid. I don't want to get into definition, but it is some kind of a topological groupoid that encodes dynamical properties of the subshift. Then you get back from symbolic dynamics back to non-commutative algebra by considering the so-called convolution algebra, which is just the algebra of compactly supported functions defined on this groupoid. And it turns out, and this is a connection that I haven't saw anywhere, so maybe this is the first time this junction is marked. It is actually isomorphic to a purely algebraic construction by taking the monomial algebra that I sketched here before, right? The monomial algebra arising from this infinite tree, and applying some non-commutative localization of it. And this turns out to be, so since this is just infinite algebra, the localization is a simple algebra. Then you pass to Lie algebras, and you have to work to show that the commutator Lie algebra is still finitely generated, simple, and of course, the most important thing is that the growth rate is remained along this journey. Just in the last 1 minute, I want to go back to our original question of growth of algebras. How do algebras, growth functions of algebras look like? We saw that there are two necessary conditions. We asked if they are in fact sufficient, and we saw that always up to some polynomial factor, and with an additional regularity condition, they are actually realizable. There are some analogs of this for groups, which are much more restrictive. I don't want to get into it. But I want to mention a remarkable result of Bell and Zelmanov, a recent result. They found an additional condition, which is necessary and is also sufficient, but it is there's a delicate point that this condition is not quite necessary because it is not an asymptotic condition. Namely, it can be that your function doesn't satisfy it, but it is equivalent to some function that satisfies it. So this gave a lot of hope and also raised the natural question whether this additional condition, which I don't mention here, it is related to discrete derivatives, is actually satisfied by all sufficiently rapid functions. And unfortunately, the answer to this is also no, in a very strong sense, that you have arbitrarily rapid holes in the space of growth function. So for any sub-exponential function, I can find some increasing, some multiplicative reasonable function, which is more rapid than it, but nevertheless, it is not equivalent to any growth function of an algebra. And just to conclude, so as far as I know, this is the first example of gaps in the space of intermediate growth functions of algebras. The previously known, well, the only gap I know, non-trivial gap I know about growth of algebras is Bergman's gap between linear and quadratic growth rate. But it is, of course, not about intermediate growth functions. And this gives the hope that maybe, well, not every function is equivalent to the growth function of some algebra, but maybe we can approximate them. So we saw that Bartoldi Smoktonovich realized any function as growth function up to some polynomial factor. Maybe, and this is a question I pose here, maybe for rapid enough functions, we can take this polynomial factor to be arbitrarily small, say n to the epsilon. And so this is the Oort cloud, the picture of the Oort cloud, which is a space dust cloud surrounding the sun. And I think this is somewhat similar to the situation here. You have some kind of cloud of growth functions of algebras around every reasonable, increasing, and some multiplicative function. And just one last remark, the situation within groups is very different. And it is believed that the situation is much more restricted. In particular, there's a conjectured gap between polynomial growth for groups, which is again much more rigid, and exponent of square root of n. And the best step known towards this gap conjecture is this remarkable result of Tau and Shalom. There's a gap between polynomial and this, well, super polynomial, but very slow function. And I think, and well, even this gap does not hold within the class of growth of algebras. So again, this I think demonstrates the difference between these two spaces, and again, the diversity and how huge and beyond our understanding is the space of growth functions of algebras. So I think this is a great point with this picture to stop. So I'd like to thank you.
Well, thank you, Barry. Everybody can. Are there any questions? Do you know famously algebras with this crazy growth?
Famously algebras of what?
Which has a very large growth.
Yes, so so for example, Freely algebras have exponential growth, but you can come up with examples of many different intermediate growth rates for Lie algebras. I think somehow for Lie algebras are supposed to be much smaller than associative algebra. In what sense? That like having linear growth for an associative algebra is almost nothing. It means that you know almost completely what the algebra is. Well, okay. But for Lie algebra, being of linear growth is even quite huge. And growth functions which are superlinear for even for graded Lie algebras is far from being able to be classified. Somehow the linear is the threshold between what you can deal with and what you cannot. I think linear growth, there are some structural results of Zelmanov and others, but more than it is hopeless.
Okay, so thank you again. And let us take a honest break of 5 minutes. I mean, okay, if anybody still wants to ask questions, it's fine. And we'll resume in 5 minutes with Aristo. כן, ואוריה תעביר לארי.
I'll take care of that. Thank you, Barry. Okay. So I see you're sharing.
Yeah. So that
okay,
works?
we can see this, yes.
Okay.
Cool. Perfect.
I'll be back in a minute.
Yes.
Same with me.
Okay.
Are we ready to start, or should we wait another minute?
I'm ready whenever.
Okay. Okay, so we are very happy to have Ari Schneidman, who joined the Hebrew University not that long ago, and we'll speak about the derivative of automorphic L functions and representation theory.
Okay, thank you for the invitation, and thanks to the previous speakers. I enjoyed the parts of the talks that I was able to catch. I'm in the US right now, so I was still sleeping at the very beginning of Nadia's talk, and I had, was making breakfast and taking a shower, so, but thank you. So yeah, for an outline of the talk, I'm gonna talk about automorphic representations and their L functions in the function field setting. And specifically for the group PGL2 or GL2. And I'll say a little bit about that, and then I'll describe geometric, the notion of a Stuka, first of all, and which is this object which really only exists in the function field setting. And I'll talk about their moduli spaces and special cycles on the moduli space. So sub-varieties or substacks of the moduli space of Stukas. And the whole point is to kind of relate the two. And so then I'll give a new formula for the Taylor series at the central point of an automorphic L function pi over PGL2, at least in certain cases, I suppose. And the formula will be in terms of the geometry, in terms of these moduli spaces of Stukas and the special cycles on them. And then at the end, if, with the little time that I have, I'll try to say something about the proof and what I like about this result. The formula is nice and it leads to some interesting questions, but I think the proof is also, it sheds some light on the geometric analog of what it means to differentiate the L functions. I'll give some kind of representation theoretic interpretation and geometric interpretation. Okay. So let's start. So just the setting. So I'm going to work in the function field setting. So X is going to be a smooth projective curve over FQ, the finite field. And so you can think, for example, P1 over, FQ, the finite field FQ. That could be X. F will be its function field. So the field of rational functions on the curve. And so in this case, in the case of P1, that's just rational functions and a variable. over FQ, so FQ of T. And I will consider automorphic representations for G, which is PGL2. PGL2 over F, over that function field. And so what is this, to say what this even is, we need to talk about the Adels. And so I'll recall that, well, you could consider the ring of integral Adels. So this is just the product over all closed points on the curve X of the local rings at each point little x of the curve, big X. So the rings of regular functions on X. And then this, for each of these local rings, this is a huge thing because I'm taking this infinite product. But for each of these local rings, I can look at their fraction field and I get the, a field, it's a completion of my original field F at the corresponding place X. And really I have to take a restricted tensor, a restricted product to get the Adels. This is the ring of Adels. And so here in each coordinate, I'm only allowing finally many coordinates where the element is not in the ring of integers. So this is the ring of Adels, and the automorphic representations I'm going to consider pi, they live inside the space of functions on G of A, G of the Adels, but functions that are actually invariant under G of F, the group of rational points of F. F embeds diagonally into the Adels because it embeds into each completion. And this big space of functions, this is the representation for G of A, because I can translate a function on the inside by the group. And pi is, I'm going to specifically look at irreducible, so cuspidal, unramified automorphic representations, so in particular irreducible. And so this word cuspidal is just the analog of a cusp form in the classical case of modular forms. I won't define it now. And this word unramified means that there's a vector in the representation pi, which is fixed by G of O, the integral points on G. So this fixed subspace is non-zero. And there's only a finite dimensional subspace of such fixed vectors as you vary over all L2, if you also demand cuspidality. And so I'm talking about a finite number of like level 1 automorphic representations when I restrict to cuspidal and unramified. These are function field analogs of level 1 modular forms, so forms for SL2Z. And so, yeah.
Level is important too?
The levels, no, just to simplify things, although exactly what level is allowed and what I talk about is somewhat important. Like the results I give will not, I don't know how to prove them for arbitrary level. And I've only written up a proof in level 1, but there's some weakening you can give. So, but certainly for exposition, it will be important. Certain things I say will be lies if I work in larger level. So, yeah. Yeah, and so, okay, this is, as I said, these are analogs of modular forms, but you might care for geometric reasons about these automorphic representations. So for example, if you have an elliptic curve over your function field F, then it's known that there's a corresponding pi of this form. And so, and you can hope to extract, well, the pi has lots of information, the same information that E has. For example, the number of points in each residue field for the elliptic curve. That kind of information is contained in pi. And so you could try to learn information about E, about geometry from pi. That's kind of my motivation for this kind of thing. Okay, and so I want to talk about the L function a little bit. And so I'll first define the nice split torus inside of my group PGL2. So this is just a copy of GM sitting inside of PGL2. And for S and a complex parameter, we have the L function, L pi of S. I won't give its proper definition. There's a proper definition, a representation theoretic definition. I'll just jump to one representation of the L function. One way to write it down. This is anyways kind of the better for actually playing with the L function, this is the right thing to use. And it's a kind of a melon transform. So I'll write something down, and you can think about how this looks like a melon transform. And maybe if you're more familiar with L functions for over number fields, like the Riemann zeta function or automorphic L functions for modular forms. And so here, phi is a well-chosen test vector. So a well-chosen vector in this fixed part of pi g of O. So I'm claiming there exists some phi such that the L function is just integrate phi, and you multiply by this absolute value of A to the S minus 1. And so this is some kind of melon transform, and this is the L function. And I didn't give you the proper definition in some sense, but the proper definition is basically, you can think of this as some kind of some generating function that keeps track of representation theoretic data. So it contains representation theoretic data just from its definition. And the hope, and conjecturally at least, and in certain cases, it's known that it also contains algebrogeometric data. But in general, it's, there are very strong statements you'd like to say, and those stronger statements are conjectural. So for example, if E is an elliptic curve and pi corresponds to E as above, so I'm going to go back up here now, then E of F is a finitely generated abelian group. The group of F rational points on the elliptic curve is a finitely generated abelian group. And conjecturally, this L function knows the rank of that finitely generated abelian group. You can recover the rank of that group from the L function. That's like a Birch and Swinnerton-Dyer conjecture for the elliptic curve. Okay, anyways, so this L function, if I complete it, so I'm gonna, when I write a curly L, I'm talking about a slightly modified L function. I don't want to give the proper definition, but if you just alter the L function a little bit, you get an L function with a nice functional equation. This is one place where the unramified assumption is a little bit important, because now I have a functional equation and the root number is 1. And I know it's not -1. That's because of my unramified assumption. And so there's this nice functional equation with symmetry about S equals 1/2. And what in the past people have done, and in general what we want, is a formula. So in certain cases, people have proven such formulas for the values of this L, the value of the L function at the central point, that point of symmetry. That's where a lot of the interesting algebrogeometric information is, but not just the value, but also the derivatives. First of all, because the value might be 0, and you might so then be more interested in the leading term, but even the non-leading terms might be interested. And we want a formula in terms of geometry, whatever that means. So formulas of this type are like the Waltz-Bourget formula, the Gros-Zagier formula. These are formulas over number fields originally, but they also have they have analogs over function fields. And most recently, so this was about r equals 0, the value without taking any derivatives. This was about r equals 1, and then Yun Zhang proved a function field only formula for general R. And so I'm going to sketch their very beautiful, really remarkable formula. They give a formula not quite for the derivatives of the L function of pi, but for a certain base change. So I'll explain that momentarily. But that's the goal, is to give a formula for the special values or the derivatives of these L functions in terms of algebraic geometry somehow. And so because I'm looking at an level 1 unramified pi with this nice functional equation, it's only interesting to look at these derivatives when r is even, because and we're looking at the special point, s equals 1/2. Let me put that back in. When r is odd, this is automatically going to be 0 because of the symmetry of the functional equation. So we'll suppose now that r is even, and I want to introduce these shtukas and the algebraic geometry related to them. So r is even, let me make the definition. So a G shtuka with R legs is so a chain of vector bundles, basically, of 2R vector bundles, the way oh, sorry, I'll go to R over 2. So I have R vector bundles, and there's some maps between them. Oops. In the middle of this chain, the maps start going in the other direction. So the central guy has maps coming into it in both directions. So the direction changes in the middle. And so you need a chain of vector bundles with these maps between them. And these are vector bundles on X. And we also need an isomorphism between the first one and the Frobenius pullback of the last vector bundle, ER. So here, each of these EIs, these are rank 2 vector bundles, on X. So if more concretely, you can just think of each vector bundle as being a family of lattices over X. So locally around a point little x on X, this is you can think of this either as a total space or just as a sheaf. And then locally, it looks like just 2 copies of the local ring, OX, which we are in the function field setting. So this is just abstractly some polynomial ring. And so you can think of each one of these as some family of lattices. And each of these FIs, we're requiring them to be an isomorphism away from at one point. There's an isomorphism away from a unique point in X. And in fact, we want the co-kernel to be rank 1, but I won't write that down. And so this is the definition of a Shtuka. It's just a kind of a chain of modifications of vector bundles together with an isomorphism, essentially identifying the first of the last, except only identifying up to a Frobenius twist. It's some kind of strange object if you've never seen it before, but it turns out this is, like for arithmetic purposes or representation purposes, is an important definition. And what the first person to do this is Drinfeld. He considered the moduli space of such things. And so we'll consider the moduli space Shtuka RG of such Shtukas. So the moduli, now what is it? It's really a stack. It's not quite like an algebraic variety or a scheme. It's really a stack. Shtukas with R legs. It's a Deligne-Mumford stack. So it's a somewhat well-behaved stack of dimension 2R. And it's a stack over the finite field FQ. So if you add a little bit of level structure, you get like a nice algebraic variety of dimension 2R over FQ, although this is actually somewhat huge. This is not a finite type. It's only locally a finite type. Okay, and the special cycles. So this is this moduli space. You can think of this as over the number field, the closest analog is something like the moduli space of elliptic curves, but this is some kind of even generalization of that. And just like there are special points in the moduli space of elliptic curves, namely like these CM points, you have special cycles in this stack Shtuka GR. So for this, we need to choose a quadratic extension of F. So a degree 2 extension of F. So that corresponds to a degree 2 cover of X, call it Y, a double cover. And I want it to be unramified for my results to hold. That's another simplifying assumption. And okay, in terms of the groups, the algebraic groups, this corresponds to a torus T. There's essentially a unique torus T in G. Namely, consider the torus of invertible elements in K. And I guess because I'm in PGL2, I mod out by F cross to get that torus inside of GL2. Okay, and now T is essentially, it's just GL1, but over the quadratic extension. I did mod out by F, but essentially it's just GL1, but over the quadratic extension. And so you can talk about Shtukas, GL1 Shtukas on Y, on the double cover, and you make the same definition as we made above, but for GL1 over Y. And you get this moduli stack Shtuka TR. It is a little bit weird because we modded it out by F cross. And so there's something kind of interesting there. But this lives over Y to the R. Shtuka G to the R lives over X to the R. These maps are just the maps that remember these unique points, XI, where the modification was taking place for the vector bundles. in the definition of the Stuka. This is the double cover, and we get a map like this, and there's a natural map. In the natural map, on points, I have a chain of line bundles on Y now, when I think about Stuka TR, like this, LR, and so on. And this map theta is sending such a chain to just their push forward. So let's give a name new to this double cover Y over X. And so then if I push forward these line bundles, then I get a chain of rank 2 vector bundles. So that's a very natural way to go from these line bundles on Y to rank 2 vector bundles on X. And this gives a map of moduli spaces from Stuka TR to Stuka GR. And this is the special cycle. So this is called the Higner-Drinfeld cycle. It was defined by Yun and Zhang. So HDTR, and this is essentially just the image. Well, yeah, it's the image of this map in some sense. It's the push forward of the fundamental class. This lives in the Chow group of dimension R, or codimension R, it's the same thing, in Stuka RG. So this is a codimension R or a dimension R cycle, algebraic cycle on the 2R dimensional stack Stuka RG. Essentially just by looking at the image of this map theta in this space. So these are the Higner-Drinfeld cycles. So these are analogues. So Higner-Drinfeld cycles defined by Yun and Zhang. These are analogues of Higner points on the modular curve in the number field setting. Okay, so what Yun and Zhang, the reason why they consider these is they use these to give their special value formula. So the Yun-Zhang formula, and I'm gonna lie a little bit about, I'll ignore kind of certain details about their formula just to try to make it as simple as possible. They give a formula for the rth derivative of pi, well actually not pi itself, but the base change of pi to k. Pi was an automorphic representation PGL2 over f. You base change it to an automorphic representation of PGL2 over k, and they give a special formula for the rth derivative of that base change L function, and it's the intersection of the Higner-Drinfeld cycle with itself. Well, it has to have something to do with pi. So they actually, you look at the pi component, HDT comma pi of the Higner-Drinfeld cycle, and you just have the intersection take place in the larger stack Stuka GR. So we have these two R-dimensional varieties, algebraic cycles, and we intersect them. We get a finite number of points, and we count the number of points. That number is, by their formula, up to some constants, which I'm suppressing. That number is the rth derivative of the L function, of the base change L function. This pi here means that we've projected the cycle onto the pi part of the cohomology or of the Chow group, because the Hecke algebra acts on the cohomology, so we can do that kind of thing. What do I want to say? Yeah, so that's the formula roughly, and yeah, so this is in some sense just it's a very cool formula. It's a higher degree analog, or it's a generalization of the Waltz-Bourget formula or the Gros-Zagier formula. It's kind of a simultaneous generalization of both, and there's hope that this has something to do with the Birch-Swinnerton-Dyer conjecture for elliptic curves over F, although it's still not totally clear the connection and how to actually prove BSD from such a formula. My formula comes from the following question: what about analogs? Is there an analog for?
Sorry, can you repeat? Pi k representation of whom is it?
Of PGL2 over k, the quadratic extension of F. So it's the base change from pi to, from F, the function VL to k, its quadratic extension.
Okay, thanks.
So yeah, the L function of pi k is really just a product of two L functions, one for the L function of pi and then a quadratic twist, two L functions over F. Okay, so I want to ask, what about analogs for sorry, maybe I'll say it this way. yeah, there's a different algebraic cycle sitting in Stuka GR. We can consider the same kinds of cycle, but for the split torus. And I'm going to call these Manin-Drinfeld cycles. So remember, A is this split torus inside of G. And so you just have, there's a similar construction where A corresponds to the split double cover. And so instead of line bundles on a double cover, it corresponds to a pair of line bundles on X, Stukas, A Stukas. And by the same kind of construction, you get a Manin-Drinfeld cycle. So also in the Chow group of Stuka GR. And this is somehow a qualitatively different kind of algebraic cycle. And this is an analog. Instead of being like a Higner point, it's an analog of the cusp, or the cusps, the cycle of cusps on the modular curve. And it's qualitatively a different kind of algebraic cycle. And I prove the following theorem. So it's, for phi, a spherical vector, so it's one of these fixed vectors in pi, non-zero. Let me first make notation. We'll define P of phi s to be this Mellin transform. So I integrate over A, phi of A to the 2 s. I'm going to do it this way. That's my Mellin transform. This is essentially, that's like a shift of the L function, basically. And the theorem says it's going to relate the derivatives of this, this guy at 0, which is the same thing as plugging in the L function at 1/2. This times the linear functional times the integral over the non-split torus. This is Waltz-Bourget's period integral. Now I want to normalize this to make it independent of the choice of spherical vector. So I divide by the Peterson inner product, which will get rid of this choice of scaling of the spherical vector. And this is equal to the intersection of the Manin-Drinfeld cycle, the pi part of it, with the Higner-Drinfeld cycle, the pi part of it. So that's the formula. So it's a formula for essentially, so the key thing is that this is essentially the rth derivative of pi itself, no base change. And on this side, there's no differentiating or anything. That's a constant, this Waltz-Bourget toric period integral. And on the geometric side, we have two different algebraic cycles, this Manin-Drinfeld cycle and the Higner cycle. And this, let me just make some remarks about this formula and explain also why it's like qualitatively different. So R equals 0, the R equals 0 version of this formula is a tautology. You unwind what both sides really mean, and you get that, of course, they're just the same. There's nothing interesting there. R equals 1 is well, because I'm in on the level 1 setting, both sides are 0. But even if you were to work in higher level, you'd get both sides are 0. And it's a consequence of the Manin-Drinfeld theorem that the cusps on the modular Jacobian, which this theorem holds in the function field setting as well, the cusps on the modular Jacobian are torsion, algebraic cycles, they're torsion. But for R equals 2, the surprising thing is that you actually get something kind of interesting when R equals 2, and something that I didn't expect. Because of R equals 0 and R equals 1, you don't get something so interesting beyond what's already known. I just would figure that these cycles are not so interesting to look at for higher R, but you get something new, you get something non-trivial for higher R. And so to see what you get and to kind of evaluate the meaning of the formula I've given above, let me just point out that this Waltz-Bourget toric period integral, this thing, you know when it vanishes. It vanishes if and only if the analytic rank of the L function is non-zero. So if the order of vanishing is greater than 0, then it vanishes. That's precisely when it vanishes. And so actually this formula, you have to break it up into two cases. you first consider, this number is what I'd call the analytic rank of pi, the order of vanishing at the central point of the L function, r pi maybe. And so if r pi equals 0, then you get a formula. The theorem above gives you a formula for the R-Taylor series coefficient by just dividing out by the toric period integral, putting it on the right-hand side. It's non-zero in that case because the analytic rank is 0, and you divide out and you get a formula in terms of geometry. And it's not for the base change L function, it's for the function itself. When r pi is greater than 0, then the left-hand side in my formula is 0. And so what you learn is nothing about the L function really, but you learn something about algebraic geometry. You learn that the intersection pairing is apparently 0. And this is interesting because these Higner-Drinfeld cycles, in this case, in general, these Higner-Drinfeld cycles are not 0. And so it tells you one of two things. It tells you either that the Manin-Drinfeld cycle is 0 or torsion, which I expect should happen sometimes, or it tells you that if it's not torsion, it has to be linearly independent from the Higner-Drinfeld cycle. And I think it's an interesting question, in my opinion. When does that happen? Because I think it will happen sometimes, but not all the time. I have a guess for when it happens. I think, well, I won't say the guess, but this leads to kind of interesting cycles, which may or may not be torsion. They're somehow different from these Higner-Drinfeld cycles. Okay, so I think I have 1 or 2 minutes. So I was going to say something about the proof, but I don't really have time to explain sort of the representation theory behind the proof. So the proof goes by Jacquet's relative trace formula. It's inspired certainly by the Yuan Zhang formula and their proof. So it's Jacquet's relative trace formula. And we're actually looking at a degenerate version of Jacquet's relative trace formula. As I said, for r equals 0, this formula above is a tautology. And, but somehow when you move to higher r, you're differentiating the trace formula, and some interesting things happen. And there's some pretty geometry, but I don't have time to go into it apparently. So I'll stop here, but feel free in the comments or just if you want to talk afterwards, I'm happy to explain the geometry of the situation. So I'll stop here. Thank you.
Okay, so let us all thank Harry. Right. Any questions?
Yeah, I have a question. Do you have any kind of argument for this of the same type for evaluating areas where for 2 MD cycles where none of them is related to the split algebra?
Yeah, so to the not and split one. Yeah, that's like a very natural question. So that's one really intriguing possibility about this formula, is the possibility that you can prove a special value formula that involves no quadratic field whatsoever. And I do think that it's conceivable that there is such a formula. It's like, that's an extremely degenerate situation. So
I meant the other way around. I meant for if A would come from K, from one real quadratic extension, and the cycle coming from a different quadratic extension.
Oh, yeah. Right. So Ben Howard and I, right. So Ben Howard and I proved such a formula. And this formula that I'm giving here, it's Jacquet's relative trace formula method. That's our method, where I use the extension that Ben and I gave to 2 different quadratic fields, like you're saying, and then we'd go to a degenerate case that Ben and I didn't cover because it's something different happens there. So yeah, the case where you have 2 different quadratic fields, that's like a Gross-Conen-Zagier type formula, and Ben and I proved that formula. Yeah. But I think what's even more interesting is trying to prove a formula for the self-intersection of the Manin-Drinfeld cycle. That I think would be really, really interesting, because then you'd be trying to prove one of the, a Gross-Zagier type formula without an auxiliary quadratic field, which would be very, very cool.
I see, thanks.
Any more questions? Okay, so let us thank Yeri again and thank all of our speakers and thank you all for coming. And the conference continues with Tamar Ziegler's talk, I think is the next.
Yeah, thank you very much. Thank you, Ari. Okay, so see you all at 5 for Tommy's talk. Yeah.
Thanks to the organizers, both of you.